We are going to learn about one of my favorite topics today, and that is proving trig identities. Before we get to that, though, I want you to do these warm-up exercises, filling in the table here. We should be able to do this pretty quickly because we should have our reference angle values memorized. And if you recall, we just need to determine what quadrant the angle maps into. That gives us the SIGN sign, and then we use the value for our reference angle. All right, hopefully you got the same results that I have in the table up there. And what we want to do is take a moment to look at the values. We want to look across the rows and see what relationships pop out of the numbers that we're getting for the very similar but not identical angles. And when we do that, we can develop our even, odd, or we can call them negative angle identities. And the first one we see is that the sine of a negative x is equal to the opposite of the sine of x. Looking at our second row, we conclude that the cosine of a negative x is exactly equal to the cosine of the same x, but that is positive. And then we look at our last row there, and we can conclude that the tangent of negative x equals the opposite of the tangent of positive x. And if we look over here, you can graph the other two cases if you want. I'm just going to graph this first case. We know here we've got our y equals sine of x. And then our second graph here is y equals the sine of negative x. And if you notice, we could take this blue one here, and we could get that blue graph by taking the red one and putting the minus in front of the sine function, because that would reflect our parent function here, parent sine function, in our midline, y equals 0, and it would produce that blue graph. A quick refresher, what is an identity? An identity is an equation that is true for all x values in the domain. Graphing both expressions produces coinciding graphs. So we have worked with identities previous to our periodic functions. One that I'm hoping comes to mind is a squared minus b squared is equivalent to a minus b times a plus b. This is an identity we've been working with for a long time, and it's true for all real numbers. Now we're going to take these identities that we've learned, and we're going to add some more eventually, and we're going to prove that the identity that we're given is either true or false. And the first thing we would do to test our validity of the identity is to use our graphing calculator. If you don't have a color display, that's okay. You still can do this. You might want to change your cursor for the second equation to a 0, and that's what I'm trying to show you here. But I'll show you how to do it on the calculator itself. So what I put in for my first equation is the first part of your Pythagorean identity that you learned, sine squared plus cosine squared. And then my second graph here is the 1, the other side of the identity. And if you want to change your cursor, you just need to arrow over until it starts flashing, and then you hit enter until you get the cursor that you want. And then when we hit graph, what will happen is this first line will graph, and then our second line, just so this is our sine squared plus cosine squared, or sine squared x plus cosine squared x. And then you can see the little bubble is tracing over that first graph, and that's graphing the line y equals 1. And this is showing that, yes, this identity is valid because these graphs coincide. If the graphs didn't coincide, then we wouldn't want to waste our time trying to prove something true that isn't true. So what we would do is to provide a counterexample. And a counterexample, we just need one of those, and that would be an x value that would cause the expressions to be non-equivalent. For the proving piece, though, let's go back to this one that we know. We would pick the more complicated side of the equation. And this definitely looks more complicated to me because I have a product, but that product is a product of two binomials. One is a subtraction and one is an addition. And what we would do is expand out this product, doing our double distributing, and then we would combine some like terms, and we would end up with a squared minus b squared. So this is the same procedure we're going to use today, but we're going to be doing it with our trig functions. Okay, something that we have to be mindful of is that you can't take shortcuts here. Everything that you write down once you choose which side you're going to work on must be an equivalent form of what you wrote down previously. So when we get all the way done, we should be able to retrace our steps and go backwards and connect every single step with an equivalent expression. So we look at this one here, and clearly this left side looks more complicated to me. It's a ratio, it's got squares, it's got subtraction. So I'm going to focus on this side. The first thing I'm going to do is use that identity that I just learned today to rewrite my denominator as 1 minus the opposite of the sign of positive theta. We want our arguments to be the same, plus we notice in our end game here, this is a positive theta, not negative. My next maneuver is going to be to use that Pythagorean identity I learned and replace cosine squared theta with 1 subtract sine squared theta, and we would tidy this up. My next maneuver is going to be to do some factoring. So I have 1 minus sine theta times 1 plus sine theta all over 1 plus sine theta. And now I'm going to divide out common factors. And then I'm left with 1 minus sine theta. And this is supposed to be a sine theta. And I'm going to bring this down. 1 minus sine theta. All right, some things that you cannot do. What you would not be able to do is to forget writing this denominator. It can't disappear through some steps and then reappear magically at the end. You also have to remember to write your argument every time. And I could definitely retrace my steps. I could go back here and see, oh, this is how I got the 1 minus sine theta. I canceled out my like terms or same factors. I can back up here and say, oh yeah, this is the factored form of this piece. I can back up here and say, oh, I used my Pythagorean identity. Oh, I used my negative angle or odd identity. All right, first question we need to ask is, do these coincide? And what we should have concluded using our grapher is that no, they do not coincide, or we could even just think about, because we should be pretty good at generating these graphs now, we've done that for several weeks, think about the transformations on the cosine function that are made on the left-hand side versus just our regular cosine. We can say right away the period's going to be different, so they're not going to be right on top of each other. So what we need to do is to provide a counterexample. So we're going to let x equals 0, and then I evaluate the left side, and I evaluate the right side, and this would be 1/3 times 1, and this is 1, and clearly 1/3 does not equal 1. All right, our next one here. Do these graphs coincide? Yes, they do. So we are going to choose either side. They both have a level of complexity. I'm going to pick the left-hand side because I can see we've got some complex fractions here waiting to be uncovered. My first step is going to be to rewrite the cosecant of x as 1 over the sine of x. And I notice I don't have any cosecants over here, so that's a good idea to do that. The next thing I see is I have a complex fraction, so I'm going to clear my complex fraction using that least common denominator technique. So then in the numerator, I have the sine of x, and then this will be over a 1 subtract sine squared x. Now I don't need any sine squared x's here, but I would need a sine over a cosine, so I think I'm going to use that Pythagorean identity again, but this time in the denominator. And then I notice I can rewrite this as a cosine x times a cosine x, and then I can see right there, here's my tangent. And then there's my cosine. So I replace sine of x over cosine x with tangent x, and I leave that cosine x in the denominator. Then I go grab this guy and bring it down. All right, our last one. Do these graphs coincide? Yes, they coincide. Both sides have a level of complexity to it. This is a ratio of two expressions. This one, though, I think looks a little bit more complicated to me, again, because I have that fraction in here, and then I also have a product. So I think I'm going to start with the left-hand side, and I'll start with rewriting this as 1 over the cosine of x. And I'll rewrite the tangent of x as the sine of x over the cosine of x. This whole thing is squared. I don't need any cosines here. I'm only going to be left with sines, and I have a common denominator. So I'm going to put everybody over that common denominator here, so that I'm just dealing with one term that I can square. And then I know my properties of exponents. I can square my numerator, and I can square my denominator. And then I'm going to use that Pythagorean identity again. This time on my denominator, I have 1 minus sine x squared over 1 minus sine squared x. And I'm going to factor that denominator. into 1 minus the sine of x times 1 plus the sine of x. And now I'm going to use my properties of exponents again. I have the same base, so I'm just going to operate with the exponents. And this would be a 2 minus a 1. And I'd be left with 1 minus the sine of x over 1 plus the sine of x. That's exactly what I needed. So I'm going to go back to the top and bring that one down.